Okay, good afternoon, everyone, and thank you for coming to this session on Geodesy and the United Nations Sustainable Development Goals. We have 4 talks today, and the first talk is an invited talk, so it's going to have a little bit more time, and then we'll move on with each of the talks. We're not going to take any sort of break in the middle, but we will have time for questions after each of the talks. If you can type in your questions in the chat, and then we can go through them there. So without further ado, I'd like to introduce our first speaker, Tom James.
Hello, I'll share my screen and hopefully grab the right one here. So does that look good, the title page? And am I coming through clearly?
Yes.
Great, okay. So my name is Tom James. I'm a scientist with the Geological Survey of Canada. And I'm working with some people from the Canadian Geodetic Survey and also my grad students, Connor Brierly Green and Max Lauch. And what I want to talk about today, I'm going to focus on sea level change as one component of the bigger problem of climate change and how geodesy contributes to that. Some of my comments will be global in nature, but I'm largely going to focus on some work that we've been doing within Canada to generate robust sea level projections that are up to date and embody the best available information. And let's see if I can advance the slide. And there we are. Okay. One thing is advancing, but not the other. So now, there we are. Okay. So my outline today is, first of all, I'll explain what the United Nations Sustainable Development Goals are. And then we'll talk a little bit about sea level change as a climate change hazard. And then the majority of my talk, I'll discuss geodesy and sea level change, and we'll kind of move from the global to the local and moving from present day monitoring to projections. Spend a little bit of time talking about development of sea level guidance for Canada, and then some prospects looking forward for how the sea level projections might be improved. So the United Nations Sustainable Development Goals. These are known as the global goals, and they were adopted by the United Nations in 2015 to end poverty, protect the planet, and ensure that by 2030, all people enjoy peace and prosperity. The Sustainable Development Goals, there are 17 of them, and goal 13 is climate action. Take urgent action to combat climate change and its impacts. And just to put some context on what I'm going to speak about, I will talk less about the impacts of climate change and more on sort of understanding climate change, the information that geodesy provides to better understand, in particular, sea level change, and how this also contributes to our understanding, improving our projections of sea level change. So my talk today is sort of focused on the front end of the knowledge chain of understanding the actual issue better so that we can assess the impacts and then take appropriate actions. So sea level change is a climate change hazard. And what it comes down to is flooding. And all 3 of Canada's coasts are susceptible to flooding. On the left is a picture from Nova Scotia. That's Yarmouth in the background. The center slide is from British Columbia, and the picture on the right is a flooded access road in Tuktoyaktuk in the Arctic. So all 3 of Canada's coasts are susceptible to flooding. And the impact or the importance of sea level rise is that as relative sea level rises, the frequency and severity of storm surge flooding will increase. And I'll discuss that in a little more detail. But first of all, let's take a look, without asking how these projections got generated, let's take a look at a few things that we know about sea level change. So, and these are plots of global sea level change, so averaged over all of the world's oceans. And what we know is that sea level is projected to rise under all emission scenarios. We have going from a low to a high. And we know that climate scenarios with larger emissions project larger amounts of sea level rise. And the connection there is pretty direct. Larger emissions means more carbon dioxide and other greenhouse gases in the atmosphere, therefore trapping more heat. Therefore, atmospheric temperatures are larger. That temperature is transferred to the ocean, and the ocean warms and expands. And those warmer atmospheric temperatures also promote larger glacier and ice sheet melt. And they also, through a number of indirect processes, promote larger amounts of discharge of ice into the ocean. So this is all well known and understood. And the consequence for flooding is that when relative sea level is projected to rise, the frequency and severity of storm surge flooding will increase. And the plot on the left is a specific example for Halifax, where 40 centimeters of sea level rise, which is possible at the upper end by 2050, moves a flooding event that has happened historically on average once every 50 years, so a 2% probability of it happening in any given year, to once every 2 years, or a 50% probability. And on the right, you see a statement from the 6th assessment report of the IPCC. This is from the Physical Science Basis Working Group 1, which was released last August. So saying essentially the same thing, but globally. And there's also a comment in here, which I won't discuss any further, but a comment about coastal erosion along sandy coasts. So that's the impact of sea level rise, is its effect on flooding. So now let's look in a general way at geodesy and sea level change. And we'll start by looking at global sea level change. And geodesy, especially satellite geodesy, provides enormous contributions to our understanding of sea level change. Here shown is a map of the rate of sea level change from satellite altimetry over about the last 3 decades. And you can see there's really substantial spatial variability, but on average, sea level has risen by a few millimeters per year over all of the world's oceans. So this is from satellite altimetry largely, and then constrained by tide gauge trends at coastlines. And of course, the game we play in the sciences is to approach a problem from as many different directions as possible, measure as many of the components as we can, and ask, are we able to build a self-consistent picture? And the answer with regard to the present day sea level budget is that the picture is quite self-consistent. Error bounds are pretty well known, and everything hangs together. So another component of the picture in terms of understanding present day sea level change are direct measurements of the mass change of the glaciers and ice sheets. And shown here is Antarctica from the GRACE satellite gravity mission, gravity recovery and climate experiment. And kind of 2 things going on here. And one of them is that Antarctica has been losing mass over the last 2 decades, and it's losing, and more recently, it's been losing mass faster. And then the second thing is this area of West Antarctica facing the Amundsen Sea and containing the Pine Island Glacier and the Thwaites Glacier is the area of present largest mass loss. And it's this, so again, a satellite gravity mission that's providing this kind of information. And a third kind of information where Canada has played a large contribution through its RADARSAT-1 and RADARSAT-2 missions is discerning ice sheet surface velocity. So we now know, when I started my career, we thought of the Antarctic ice sheets as these sort of static blobs of ice. And we now know that there's this enormous complexity, that there are ice streams where ice flow rates are 10 and 100 times larger than the background rate. And this is shown in this picture here, based on data from a large range of synthetic aperture radar satellites, plus a bit of Landsat and so on. So these contributions from geodesy in terms of understanding present-day ice mass change and sea level change are enormous. And then what is done is that this information on present-day changes serves as a kind of a boundary condition for models that project forward into the future, where we have these scenarios, which in this figure are expressed through these SSP, shared socioeconomic pathways scenarios. And they make assumptions about how much carbon dioxide will go into the atmosphere. That determines projected atmospheric warming. That heat is transferred to the ocean, which causes the surface layer to expand. And it also causes glacier and ice sheet melt. And so sort of through this chain of processes, we arrive at a figure like this, which shows projected sea level change up to the year 2100. And most of these scenarios, projected sea level change is less than a meter by 2100. But there is also the possibility of instability processes operating on the Antarctic ice sheet that could cause larger amounts of sea level change. And I'll come back to that again in a few slides. So I've already mentioned most of this. The first bullet describes the various contributions to global sea level rise. It's important to realize that because of gravitational effects and ocean currents, these effects are not uniform. So global sea level actually varies from location to location. You can think of global sea level as being referenced to the center of the Earth. What we actually care about is relative sea level, where we also factor in vertical land motion. This is the sea level that we experience at the coastline. It affects infrastructure, it affects our valued activities, and it affects ecosystems. And the way to think of this, of course, is that if global sea level is projected to rise by 50 centimeters at a particular location over a given time frame, and over that same time frame, the land rises by 20 centimeters, then the relative sea level that you're going to experience is only 30 centimeters. And so factoring vertical land motion into projections of relative sea level change are very important. And this is one of the things that I've been working with Geodetic Survey over the past decade or longer, is to take the best available information on vertical land motion and then information from the IPCC, the Intergovernmental Panel on Climate Change, to produce tailored sea level projections for Canada. So in Canada, where does this vertical land motion come from? And of course, in places like the Fraser Delta and the Mckenzie Delta, there's local effects, there's subsidence, consolidation. But over most of Canada, the vertical land motion is due to this process called glacial isostatic adjustment, where the ice during the last ice age pushes the surface of the Earth down, the mantle flows viscously deep inside the Earth, and then after the ice is gone, the lithosphere recovers to its former state. And that's what's causing these this vertical land motion. And here is a map showing vertical land motion from the Canadian Geodetic Survey land motion model. And it's constrained by GNSS observations on bedrock, so Global Navigation Satellite System observations, and informed by predictions of glacial isostatic adjustment models. So particularly in the north, the GNSS network is fairly sparse, and we use these model predictions to interpolate in between. And so this is the land motion model that we use with the latest information from the IPCC to generate relative sea level projections over Canada. And here again are the global sea level projections. So we have the vertical land motion from the previous slide, and then the global projections, which are actually provided in grid form, because as I said, these global projections do vary from one location to another. And this is just the globally averaged plot to generate projections of relative sea level change. And here is a very high emission scenario, SSP 5-8.5, and this is the median projection. So it's not the highest possible at the year 2100. One of the changes between the fifth assessment report and the sixth is that these projections are now provided through the 2150, and we'll be able to use that information. So now let me switch gears a bit to talk about the development of national sea level guidance. And one of the things that's motivating this, okay, afraid of that. Now, I can't use my mouse, it will make things go forward. Anyway, focusing in on this low likelihood, high impact storyline that includes ice sheet instability processes. This has been known for quite some time. It's been incorporated into national guidance of different countries in different ways, sometimes attaching this kind of information, attaching a lot of weight to it in other countries, other situations, taking much more of a wait and see attitude. But it's because of this low confidence but high impact possibility that the development of guidance seems like an important thing to do. So now let me talk about this sea level guidance for Canada. And the context is that coastal regulations are provided by provinces and territories. But so we started this process by contacting the provinces and territories to see if there was interest in a national process. And the answer that came back was a resounding yes, because it could provide some uniformity, national uniformity in sea level guidance, as long as adoption of the guidance is voluntary. And we recognize that many coastal areas are at high risk because of the impacts of sea level rise, as I've already mentioned. And one of the factors that drives this is that we know that early adaptation, it reduces not just future costs, but also current and near-term costs. And it's recognized as being very cost effective, with sometimes return on investment ratios of 10 to 1 and better. We also recognize in developing the sea level guidance that the scientific uncertainty is going to persist, at least for a while, at least for 5 or 10 years, and possibly through all of our lifetimes, because these processes are these ice sheet instability processes. They're hard to study. Some of them have a kind of an element of a threshold where once you meet a certain point, then things can accelerate. And being able to say when a threshold will be reached can be very difficult. So we expect the scientific uncertainty to persist. And we know, therefore, that we've got to carry out or consider robust adaptation responses and treat adaptation as a process, something that is continuous and is evolving, and not a product, not something that you do once. I'll just spend a few slides. I think I've got about 10 minutes left.
Yeah, that's correct.
Okay, so I'll quickly go through a few slides on an international survey on future sea levels, because it's helping to inform this development of sea level guidance. And we started off by trying to understand the present state of sea level planning in Canada. So, asking the question, do you have guidance materials or policy documents that address future sea levels? And we actually got 5 respondents that answered no. from Atlantic Canada and Northern Canada. And this response is a little better than the global average. This is an international survey that involves over 20 countries, and it's led by some researchers from the US. You know, what's the title of your primary source? Every jurisdiction came back with a different title. Not to say that some of these sources would have, if you tracked it back, would have a common source. But one of the things that really stands out is that sea level guidance in Canada presently is drawn from a very wide range of sources. We were interested in whether the guidance had been co-produced between the stakeholder or practitioner and the, if you will, the scientific authority. And the reason for this, the reason we were asking this question is we were curious as to the degree to which the guidance was, you know, usable and consistent with the needs of the practitioner. And we found that a relatively low number, shown in bold here, was it co-produced. We hope that through this process we'll increase that percentage of jurisdictions that report that their guidance is co-produced. And you look at sea level projections beyond the year 2100. And yes, some do. They all come from British Columbia. Not coincidentally, British Columbia has guidance that goes through to the year 2200. And I think the takeaway from this is that if you provide information on a longer time frame, that information will be considered. So some useful information there from that survey. I just skimmed a few interesting points. We actually asked many, many more questions. So returning to the development of the National Sea Level Guidance, we have a steering committee. What we're doing, we're in the process of discussing the AR6 projections and then sort of considering the advice or guidance that we would provide about how to use these projections. And it's, to some extent, it comes down to, or, you know, a large question is, should you be looking at that high end or not? Or are you fine with looking at the medium confidence projections? And so with that, I'm coming near the end. I'll just, a few thoughts on looking forward with geodesy, sea level change, and so on. And so, you know, asking, how will geodesy help constrain future sea level projections? And by doing that, contribute to United Nations Sustainable Development Goals. And I think that the broad response given in this first bullet is that geodesy is going to continue to be this enormously important discipline to contribute to the continued monitoring of oceans and ice sheets through a number of methods, altimetry, gravity, INSAR, and others, to provide the best possible current information on ocean height changes and on ice sheet mass change and flow. And I should also have included in this bullet glaciers. No, it's not just ice sheets, it's also glaciers. And I'll spend just 2 or 3 more slides considering the second bullet. You know, have we done everything that we can with regard to the vertical land motion component? And the answer, it turns out, is not quite. The geodetic survey crustal velocity map that I showed you earlier is largely considering, so it's using the measurements of present day land motion, but the models that it was using of glacial isostatic adjustment were the models from the last ice age, and not considering more recent ice mass changes, such as from the Little Ice Age. And of course, we have mountain glaciers in the coast mountains. We have ice caps and ice fields and glaciers in the high Arctic. And one thing that we really haven't looked at yet are the effect of these more recent ice mass changes on crustal motion. And so this is work of Max Lauch, who defended about a month and a half ago. And this is his study area. The light blue are the coast mountain glaciers. And this is one of the results. He actually looked at a large number of reconstructions of the coast mountain glaciers, but this is a representative one showing the predicted crustal uplift with a peak uplift of around 12 millimeters per year. When you look at the different models, it ranges from 12 to 14 millimeters per year. But if you look at the green stars, that's where the GNSS or GPS is. And you can see that one of the things that we would hugely benefit from are some additional GPS sites within the coast mountains to better constrain these models. But at any rate, this pattern of uplift is constrained by coast mountain ice sheet history. We think we've learned a lot already. And results like this can inform future versions of the National Crustal Velocity Model and then contribute to future revisions of sea level projections. And so with that, I'll summarize with just 2 points. Geodesy provides key information for monitoring and projecting sea level change, projecting climate change, including sea level change. And this contributes to the United Nations Sustainable Development Goal 13, which is the climate action goal. And with that, I'll stop. Thank you very much.
Great. Thank you very much, Tom. I think it was a really nice introduction to the session because you also introduced the United Nations Sustainable Development Goals and how they relate to Geodesy, which is why we're all here. So with that, I will take questions. You can type them in the chat, or I think you have the power to unmute yourself. So you could do that as well, since we're a fairly small session. So does anybody have any questions for Tom?
Oops.
Yeah, go ahead.
Yeah, on the vertical crustal motion plot you showed, there was a big positive on the west. I don't think you talked about it. I was just curious as to what that was.
Yeah, okay. So that's a big positive. Oh yeah, I think I know what it is. That is Glacier Bay in southeastern Alaska. And that in and that's been well studied. There's GPS there. There we are. So it's I assume you're referring to that blob.
Yeah.
Yeah. So yes, that's Glacier Bay, and that's some local glaciers in Alaska that have been losing quite a lot of mass. Well studied, well understood, and frankly, you know, one of the motivations for the study that we undertook in the coast mountains, in the coast mountains. Papers by Chris Larson, Jeff Freimuller, and a few others discuss that.
Yeah, thanks.
Are there any other questions? So Tom, in that region, they do have quite a dense network of GPS stations, correct?
Yeah.
Yeah.
Yeah,
nice
we need to. I'll let's see if I can find my mouse. I've lost my mouse. Oh, there we are. I'll cycle back to Max's work, and we can look at that map. So you know, we've got that GPS. So that's Whistler. That's rising at about 4 millimeters per year, and this is Quadra, close to Campbell River, rising at 4 millimeters per year. And in essence, those are the two sites that are constraining our models. You know, we'd love to, like if we could only put one site in, you know, put it where we expect the signal to be the biggest, which would be right here. But we've actually, you know, there was a workshop about 3 weeks ago, considering an expansion of geophysics infrastructure in Western Canada. And if you can be a little more ambitious, you know, you'd like a few sites running up and down the axis of the coast mountains, and then at least one running across, because there's, you know, there's a lot of earth structure here, differences in the effective lithospheric thickness. We expect in general the asthenosphere to be quite fluid, but up here, there's a bit of a slab window, and there's some recently published results from Patagonia that under a slab window, mantle viscosity, you know, instead of it being 10 to the 19 Pascal seconds, which is already small compared to Hudson Bay, is 10 to the 18, you know, another factor of 10 smaller. So do we have slab window effects going on up here that would be sensitive not to centennial scale ice mass changes, but actually decadal scale. So tons and tons of stuff to dig into, but we need more observations for sure.
That could be the topic of another session in Geodesy. Thanks, Tom.
Yeah, well,
So
you're very welcome.
With that, we'll move on to our second talk. So I think Calvin or Christine, you can share your screen. So the second talk is going to be presented by two presenters, the co-convener for the session, Calvin Klatt and Christine Hirschkon. I think she's starting first. So when you're ready, go ahead.
So can everyone see the screen okay?
No. Oh, now we can.
Calvin, did you have a few words, introductory words?
Well, I just wanted to mention, yes, so this will be a joint presentation of myself and Christine Hirschkorn from Natural Resources Canada. We're both involved in the UN, these UN activities that we'll describe. So I think Christine will do the first part and then I'll jump in towards midway through. So go ahead, Christine.
Thanks, Calvin. So the presentation is about the United Nations Committee of Experts on Global Geospatial Information Management. It was established by the UN's Economic and Social Council in 2011. So we're coming into just over a decade of this work. The UNGGIM is led by United Nations member states, so who have the voting rights that drive the agenda of the committee. It's considered the apex government-driven global body for geospatial information management, and it encompasses a very wide range of geospatial domains. So obviously geodesy, but other things like land administration, marine, for example. And increasingly over time, we've seen that the UNGGIM has oriented its objectives and its work towards supporting the Sustainable Development Goals.
Christine, we're not seeing the full size, we're seeing the notes and the...
Oh, that's interesting, because I am seeing the full slides.
Okay. It's not a big deal, actually. We do see the notes at the bottom.
Oh, my apologies. I am honestly not quite sure. If anyone has a quick tip to offer. Yep.
Christine, it's Tom. You could unshare, and then when you share again, look really carefully that you're sharing. I assume you have more than one monitor. Make sure you're sharing the monitor that has the slideshow version, if that makes any sense to you.
Yeah, no, I thought I did that, but let me try again. So, okay, actually give me one moment. I'm going to make sure that my screen is on the slideshow first. And now it's frozen. Is my screen visible at all to anyone right now?
Christine, we see you.
Okay, let me try this.
I think you got it.
Yeah, that works.
That works? You can see
Yeah.
it?
Yeah.
Okay.
Yeah, it looks good.
Okay, so now I'm seeing the note slides, but it's better this way. Okay, my apologies. Let me try to catch up some time. So I won't go into detail on the Sustainable Development Goals, just to note that that's the 17 of them there. The two, I'd say, basic roles of geospatial information services is to support the attainment, support national governments, obviously, to align their activities to support attainment of the SDGs, and as well, geospatial information features in reporting on the Sustainable Development Goals, although reporting is largely driven by national statistical organizations such as Statistics Canada. So due to the fact that UNGGIM is considered a technical committee, Global Affairs delegated the role to Natural Resources Canada. And where I'm located at the Canada Centre for Mapping and Earth Observation, my Director General, currently Eric Loubier, is the head of delegation on behalf of Canada. But of course, we are joined by delegates such as Calvin Klatt and other colleagues in other parts of the Government of Canada to form the Canadian delegation. And although the delegation is, the UNGGM is led by member states, there are opportunities, there are observers who participate in the UNGGM. So that includes the private sector, civil society, and academic networks. And as you can see, here is the academic network. It's considered one of these thematic groups. There are also regional.
I hate to do this, but we were looking at the 17 boxes still.
Oh my goodness.
Okay.
Yeah. Can you? My apologies. The problem is I now have so many screens open that I can't tell which one is doing what. Okay.
And now we see.
Is this better?
We see participation, yeah, and now the academic network. Yeah.
Okay, my apologies. So the academic network is one of the thematic groups, and the other point to note is that there are also regional groups in the UNGGM. Canada belongs to the Americas regional group, and there is also an academic group working within the regional group, and that's actually where I've seen the most activity and collaboration related to learning activities and capacity development. So for us, we see many benefits to Canada's participation. In large part, it's to facilitate sharing of resources, global best practices. It's a great networking opportunity for us, and it also provides us the opportunity to influence global principles, for example, related to open government, Indigenous sovereignty. And this slide is just to show you the, I'd say this is the flagship publication of the UNGGM, the Integrated Geospatial Information Framework, that contains a lot of information to support nation states to develop their spatial data infrastructures. And this is all available on the internet, if that's of interest to folks. And this is now the transition slide. So this is an example. These are the functional groups that are largely driven by member states. And so you can see the range of topics. And Calvin will now speak to the subcommittee on geodesy.
Thanks, Christine. So, so I guess if we look at these functional groups, sorry, go back to the functional groups list. You'll see that there's only one subcommittee, but there's expert groups on a couple of different areas of interest. So, for example, Natural Resources Canada Surveyor General is interested in the land administration, which is one of the expert groups. And then there's working groups. So there's actually quite a large scientific component to the disasters area, as well as the marine geospatial component. But anyway, we'll focus now on the subcommittee on geodesy. So next slide. So the subcommittee on geodesy has kind of, in a way, similar goals to the overall global geospatial information management. It's an intergovernmental forum. It's really encouraging things like open data sharing, et cetera. It advocates for guidelines, standards, and there's a very big push for capacity development of other nation states who maybe are not as advanced as Canada in terms of geodetic infrastructure. And there's obviously outreach advocacy. So you'll see I've got kind of number 1, 5, 6, 10, 11. So this is a subset of the longer list, but I think it kind of captures the overall objectives, and it's very similar to, I think, the GGIM in general. So next slide. So for the subcommittee on geodesy, it's the representation is nominated by the regions. So the UNGGM Americas creates a slate of candidates that they submit, and that list includes Canada and the others that you see there. So Canada is a member now of the subcommittee, and then we have taken, taken on a role as a member of the Bureau. So there are only 9 nations in the Bureau, and the Bureau is kind of the central body that really coordinates and drives forward the work of the subcommittee. And so when Canada is named as a member state, Canada then assigns that work to someone, and that someone in this case is myself. Next slide. So Canada is then a member of the subcommittee, and the subcommittee has several focus areas. So these are kind of working groups within the subcommittee. Canada has contributed primarily to the third and the fifth ones here. So policy standards and conventions was led by Dr. Mike Kramer of Natural Resources Canada for the first few years, and then he passed it on to a different leader. So he no longer is running that effort, but he has remained as an interlocutor for the ISO, and in particular, he's interested in promoting and making sure that the ISO Geodetic registry is sustained on an international basis. Canada is also contributing to the communications and outreach efforts, and that's work that's done by Bianca Dau of, again, Natural Resources Canada. So this is the Geodetic Survey Group. And then I guess what's not shown here is that work on the Bureau where I'm involved personally. Next slide. So this is kind of a slide that is taken from an Earth Day presentation, and you'll see a graphic of the development goals. And in the core, my geodetic colleagues have put the global geodetic reference frame at the center of the circle. But if we look at the list of items here, we see many things that would have been discussed at this conference. So hydrological water quality, oceanographic observations, land cover, land use, elevation, topography. So there's a very strong tie between the activities in the geosciences and the sustainable development goals. Next slide. Just mentioned that one of the key things that has been done in the UN front is this resolution by the General Assembly. The General Assembly in 2015 passed this resolution that declared basically that the global geodetic reference frame is for sustainable development, and it mentions ground-based observations, satellite remote sensing, and the benefits of that. So this is kind of it's a political statement more than anything. It does press nations to abide by some of these general guidelines, like sharing of the data. But it's a powerful statement, we believe, about the importance of geodesy for sustainable development. Next slide. What's coming up in the near future is a Global Geodetic Center of Excellence. It's a UN body that it is going to be located in Germany, and it is funded by Germany, but it is a UN body that it will abide by UN regulations. Employees will be UN employees. And it will primarily, I believe, push international collaboration and sustain some of the standards work, but also a lot of work on capacity development in education, training, capacity building in developing states. So that's coming up. Apparently the lawyers have just recently agreed on the language, but the documents have not been signed. So it's very hot off the press. And the next one, I think I have a little list of other kind of activities that are being done. One thing that's a bit of a coup is that Ambassador Peter Thompson, who is the UN Secretary General Special Envoy for the Oceans, has agreed to be a global geodesy ambassador. And in that role, he's given presentations at different events and is supporting the overall needs for, supporting our overall initiatives related to the field of geodesy. Earth Day 2021, there was a major event where we attracted sort of senior managers, kind of director general level people from across the globe to an event during Earth Day. And it was the power of where, the value of, I can't read the title, but of geodesy to society, I guess. And that's the language that was used. There was a follow-up event in 2021 for the Americas where we, different sampling of different states discussed how governance issues and all of the infrastructure status, et cetera, for their countries, the priorities for them. That was an event that was led by Canada, because Canada is the bureau rep for the Americas. So that was interesting because I was running that event and it was all in Spanish language. And my presentation was with Spanish slides and in English words. And then I guess moving forward, the different focus groups, the work continues. So there's many different activities. For example, the infrastructure group has done surveys of national needs and as well as the needs for different geodetic services like the IGS, et cetera. Next one. And that was it. So any questions?
Great, thank you very much. So I assume, Calvin, you're taking questions in English, Spanish, and French?
Yes, that's right.
So you can type it in the chat, any questions, or you can unmute yourselves for Christine or Calvin. I just have one question regarding the involvement of different groups. Do you change them throughout the time, or have you decided on the groups and those are the ones that are being involved throughout the duration of this, or do you look every year to get different groups involved?
I'm not quite sure. So within the subcommittee, actually, there's been we're actually working on terms of reference so that we can reorient the direction and eliminate some task activities and prioritize others. So in fact, the communications one may merge with the capacity development one, for example. I think at the higher level, I'm not quite sure how it's managed. The academic network, I believe there's no coordination within Canada. I believe it's just people can apply through the network itself. And I'm not sure how that's handled in terms of reorienting or new members or things like that.
Okay, good. Thanks for that.
Christine, do you want to jump in, Christine, or?
Well, I guess it kind of depends on what you mean by the scope of new members. So I would say in general, it seems like for the various working group, expert group, subcommittees, at least for the co-chair role, which is typically a nation state role, they try to rotate every couple of years, and they typically try to have what they consider a developed nation and a developing nation present. I see more in general, more stability in terms of who the actual members are over time, because that supports the agenda when there's some history there. But every working group or expert group has its own terms of reference that define how to become a member. And so for the academic network, it's based on organizational membership or institutional membership. So a university or another type of educational institute or an academic associated with that institute would put forward an expression of interest on behalf of the organization. There would only be one institutional member for each, or one quote unquote member for each institution. But so it's possible if people are interested that their institution may already be in the working group, but that option exists to participate in that way. Great,
thank you. So with that, I think we're supposed to take a little bit of a break and start again in 8 minutes. So you can feel free to take a stretch and move away from your screens, and we will reconvene for the last 2 presentations of this session in 8 minutes. Our speaker, I guess I'll, okay, welcome back everyone. Our next presentation is by Zhengleng Wang. Go ahead.
Thanks, Georgia. Good afternoon, everyone. In this talk, I will report the progress on the development of North American Pacific geopotential datum of 2022. Does my slide move? Okay. First, I would like to introduce development team, then define what the CGBD 2013 and the NAPGD 2022 are. The rest presentation going to focus on development of 2 experiment geoid model for NAPGD 2022. The 3 development team: Canadian Geodetic Survey team led by Mark Werner, a National Geodetic Survey team led by Yanming Wang, and the INAHE counterpart of CGS and NGS in Mexico, led by David Avalos. So what is CGBD 2013? Full listing of CGBD 2013 is Canadian Geodetic Vertical Datum of 2013. It is official highest datum in Canada. It was defined by equal potential surface representing the coast mean sea level for the North America. It was realized by a geoid model, which represents the equal potential surface. And it allows us to convert GNSS measured ellipsoid heights, such as GPS measured heights. And osmometric heights are the heights compatible with published elevation on benchmark and the topographic map. The pen on the right side shows the relation between those three types of heights. Lowercase h represent GNSS heights, uppercase h osmometric heights, and represent geoid. So geoid model is used to convert GNSS measured heights to the osmometric heights we normally use. New datum basically stay same definition as CGBD 2013. The difference lie in the realizations. The new NAPGD 2022 gonna use geoid model 2022, and also new datum also include a dynamic component, take into consideration time variable geodetic change, and the epoch going to be different. New datum going to be 2020. Our rest presentation is about two experiment geoid model developed from this by those three teams. So those two models use common data include terrestrial gravity data, airborne gravity theory block from airborne gravity project, and a new digital elevation model, and the satellite altimetry DTU marine gravity grid. ArcGP 2020 gravity grid provided by National Geospatial Intelligence Agency, and the two Earth gravitational model, XGeoid Ref A and B, developed by NGS. The map on the right side shows the Hermit gravity anomaly grid of one Archimedes built from this common data sets without include gravity data. This Hermit gravity grid is used for geoid modeling in Canadian geodetic survey. We used 63 gravity airborne block for these two models. Left side map shows the spatial distribution of these 63 airborne blocks. Gravity project still ongoing. US NGS planning to cover whole entire United States territory use airborne gravity. Right side map shows the gravity disturbance derived from this airborne gravity datasets at heights of 6,000 meters. We also built a new digital elevation model of 3 arc seconds, or about 100 meter resolution. The data source include USGS 3 DEP model and Tandemax and Maris as showed in this map. This new digital elevation model is validated against GPS on benchmark in US and Canada. RMS difference between those GPS benchmark between DEM and GPS leveling is 2.1 meter, comparing about 3 to 5 meter for the previous digital elevation model. We also compared geoid with or without airborne contribution. This map showed airborne contribution to the geoid model. It ranged from a few centimeter to decimeter. The area show major update or major change at area. The gravity coverage are poor. CGS and NGS use different methods for geoid modeling. CGS use Stokes Hermit for geoid modeling. That has been done for decades. And NGS use Molodensky and RTM approach for geoid modeling. And another major difference between two agencies is we constrain our geoid model at low degree to the satellite model, while NGS use high degree EGM to constrain their geoid model. Both agencies have developed two models called Model A and B. Model A doesn't include airborne. Model B does. This map shows the comparison between the A model. We can see difference range from a few centimeters to a few decimeters. A major difference are shown over mountain region. The difference over Greenland is because ice correction. CGS model include ice correction, while NGS does not. The difference over Mexico and Central America still to be understood. Same comparison also has been done for Model B. For Model B, CGS applies slightly different approach, which more comparable with NGS approach, which we modify kernel much higher degree to use EGM model more. The model getting similar, but still we can see decimeter difference over mountain region. And we zoom in Colorado region for the worst scenario case. So as we can see, the difference between the NGS and the CGS model, RMS difference, is about 3 centimeters, but the range of distance still can reach to a few decimeters. Based on the two sets model, A and B model, we developed two experimental geoid model called experiment geoid A and B, cover whole North America. And those two models tested against the GPS leveling in 3 countries. And the standard deviation of the difference range from 14 centimeters to 30 centimeters. Most also those differences are because of long wavelengths or long baseline systematic error in leveling data. To avoid those systematic error, another test was done state by state and only based on the baseline shorter than 100 kilometers. The standard deviation range from 2 centimeters to about 5 centimeters. And in case of Canada, is here about 3.6 up to 3.7 centimeters. US NGS established 3 called geoid slope validation line for 3 types of terrain. GSVS11 for the flat Texas, GSVS14 for the moderate terrain in Iowa, and GSVS17 over mountainous Colorado. The GPS leveling testing result, the standard deviation range from 1 centimeter to 2 centimeters. This result gives us an optimistic view, suggesting with the area have good data, good gravity data, DEM, it is possible to achieve the accuracy of 1 to 2 centimeters. That's the target of the future North American geoid model or vertical datum. We also did the validation against satellite altimetry data over Great Lake region. Result similar to what has been shown for GPS leveling data, except for Lake Michigan and Lake area. This track 1 and 2 and track 13. Its big difference is because poor gravity coverage over Lake Michigan and Lake area data is okay, but data has been identified misused somehow, improperly used somehow. Then finally, we also developed a geoid error model for 2 experiment geoid model. And on the west side, this error range from 2 to 5 centimeter. On the east part of the continent, geoid error range from 1 to 3 centimeter. Then finally, the way forward, we still need to understand and reduce the geoid difference for the mountainous region among the solution from CGS and NGS, and in the future also in the solution. We need to combine the gravity data with satellite and terrestrial gravity data in Stokes integration by kernel modification. Right now, gravity data is built into EGM model. In the future, we will use it separately. And we need to estimate topographical reduction error at various steps. And it is in discussion if we need correct for effects of lateral topographical mass density variation. And also we need to develop dynamic geoid model from GRACE, glacial mass balance, hydrological, and GI model. And also we need variety geoid model, use new type independent data, such as new SAR mission or SAR in-SAR mission. Thank you for your attention.
Great, thank you very much, Sheng Liang. I open the floor to questions. If anybody has any questions, you can type it in the chat or you can unmute yourself and ask away.
I have a question just about the term quasi-geoid. When you had geoid, quasi-geoid, I'm just not exactly sure what that means. If you could perhaps explain.
Normally, if we use Morodansky approach, Morodansky approach called the modern boundary value problem, it gives a quasi-geoid. Because North America, we can adopt geoid model, not quite a quasi-geoid model. In North America, we use also much height. We need geoid heights. This conversion needed called geoid to quasi-geoid separation term. So what NGS doing is they use Morodansky approach to first compute quasi-geoid, then use that separation term, convert quasi-geoid to the geoid model.
Okay, that makes sense. Thank you.
Yeah, I hope I answer your question.
Any other questions? Okay, we have time for one more. So I'm just going to ask a quick question because I'm wondering, you said in Lake Erie that we know that there's something wrong with the data. Are you referring to the tide gauge stations there or the gravity data?
The tide gauge data is okay.
Okay.
In the CGS, we properly handle some of both the shape data. But NGS, even this NGA, somehow we already informed them when correction not being properly handled. I don't exactly know. The mark is the one to handle the correction.
Because we're working on something with the tide gauge data there, and I was hoping that you would say it was the tide gauge data because I would solve some of our questions. But okay,
the tide gauge seems okay. Yeah. Okay.
Okay, thank you very much. So we'll move on to the last presentation of the session. And Julien, if you want to end sharing your screen, and then we'll have Stephanie start sharing.
Okay, yes. Yeah, okay.
Okay, Stephanie, no, that's fine. Okay, so our last presentation, we're in notes view, so presenter view.
That's good.
Yep, now it's good.
Awesome.
Our last presentation is Stephanie Bringeland. Go ahead.
Awesome. Yes, my name is Stephanie. I'm a PhD student at Queen's University in the Department of Geological Sciences and Geological Engineering. And I'm going to be talking today about how knowledge of terrestrial water storage derived from GRACE and GRACE follow-on can lead Canada towards a sustainable future. So just a little outline, I'll do a bit of an introduction, and then I'll talk about the case study, which is the Mckenzie River Basin, which is, there's a Landsat image of the Mckenzie River Basin in the background of the slide, which is a very complex hydrological basin. I'll talk about some observations from the case study and then ongoing and future work. So a bunch of presenters have introduced the Sustainable Development Goals. There are, of course, 17. In this presentation, I'm going to focus on 4. So life on land, climate action, clean water and sanitation, and partnerships for the goals. So 2 main objectives I'm looking at. First, to investigate long-term trends in terrestrial water storage in the Mckenzie River Basin looking at precipitation records, stream gauge stations, and of course, GRACE data. And then second, I'd like to connect this trend analysis with the Sustainable Development Goals, namely looking at opportunities for impact that this kind of trend analysis from Geodesy can have on the goals, specifically in the Mckenzie River Basin.
Stephanie, I'm just going to interrupt you for a second. We just
Yeah.
had somebody request that you speak a little louder. I think your audio is a little weird.
Oh, okay, I can switch my microphone. I think it's on my headphones right now, so I can.
Okay.
Does that help?
Yes.
Okay,
Okay.
excellent. That must be it. Wonderful. Thank you. Yes, so the Mckenzie River Basin is Canada's largest. It covers 3 provinces, BC, Alberta, and Saskatchewan, as well as 2 territories, the Northwest Territories and the Yukon. It's not a highly populated basin, but it has rich ecosystems, and many Indigenous communities have lived in this basin for thousands of years. It's mainly boreal forest and tundra, and it is the leading source of outflow into the Arctic Ocean, which means it plays a major role in regulating ocean circulation and the Arctic climate. So I'm going to go through just a few local examples local to the Mckenzie River Basin for each of the Sustainable Development Goals, just to sort of go through the motivation behind this study and this case study in particular. So first, looking at the WAC Bennett Dam, which created the Williston Lake Reservoir. It was finished in 1968 and was a huge win for hydropower, obviously a very renewable energy source. However, it did affect a lot of people and a lot of ecosystems. So it flooded about 350,000 acres, including traditional Tsikini territory, which these communities are still being impacted today and still recovering from the effect of that dam. So it's definitely a case of life on land being impacted by some policy or architecture or construction. As well, animals that are dependent on the wetlands, like muskrats, have been affected. However, beavers, which are also wetland dependent animals, are experiencing increasing populations. There have also been increasing notes of unhealthy fish populations and certain types of salmon appearing in rivers and streams that they never have before. So there's definitely changes happening to the life on land in this basin in recent years. As well with number 13, climate action, looking at permafrost thaw. Many people in this conference already have talked about permafrost thaw in Canada's north. Specifically in the Mckenzie River Basin, we have, of course, biogenic methane, but also a lot of sources of geologic methane because of the vast amounts of oil and gas reserves in the basin. And this is a problem when the permafrost thaws and it has a path to the surface, and it can be released in larger quantities and greater speeds. Another thing associated with permafrost thaw is catastrophic lake drainage. So similarly to the methane escaping, as permafrost thaws and the lakes can find new outflow paths, lakes can drain quite quickly, even in as little as a day, which can be 1, dangerous for people downstream, and 2, have a great impact on the local ecosystems as well. Another thing to do with climate change, Arctic outflow, of course, is significant from the Mckenzie River, and the warmer the water leaving the Mckenzie Basin, the more it will accelerate ice melting in the Arctic as well. So in terms of clean water and sanitation, the basin is home to a lot of industrial activity, which can introduce contamination to the surface waters. There's also increased concentrations of ions in surface water, which have been associated with melting permafrost. So the mainly dissolved salts attributed to the groundwater coming from permafrost thaw. There's also been changing levels and surface water levels, and this is quite variable depending on the region. Some areas are experiencing large declines where others are increasing. And so it's difficult to pinpoint a long-term trend for all of it, but looking locally, we can see levels changing quite rapidly. Finally, partnerships for the goals. In terms of the partnerships and the stakeholders in the Mckenzie River Basin, as I mentioned, there are a lot of Indigenous communities who hold a lot of traditional knowledge of the region. And so collaboration with Indigenous communities is vital to make sure that the impacts of policies or construction projects, the impact is mitigated. As well, and this is kind of a fun part of this conference, which is a big, collaboration and meeting of scientists working on Canadian projects. We need to effectively communicate these things so that government policy can respond accordingly. And of course, this happens on a number of different levels. The Mckenzie River Basin covers several provinces and territories. So any policy that is put in place to that is for the Mckenzie River Basin needs some collaboration as well. So the data I'm using is GRACE and GRACE follow-on data, specifically looking at the MASCON products produced by CSR and JPL over a 2002 to 2020 time span, which is going to apply to all of the data sets I'm using, even though some of the precipitation, gauge station records, et cetera, do extend further historically. But for the data assimilation, I'm just using that limiting time span. Going over the methodology, so the data, again, I touched on the GRACE data already, but for precipitation, I'm using the CRU, CMAP, and NOAA gridded products. Snow depth using the Geodesy snow water equivalent gridded product, and for surface runoff using gauge station records from the hydrological database. Then I'm applying a 400-kilometer radius Gaussian smoothing function, and that's in order to reduce spatial leakage into the basin from other basins and from the ocean as well. And then for the surface runoff, I'm calculating a weighted average proportional to the drainage area of each gauge station. Then using regression to apply or to remove the seasonal and interannual signals from the GRACE data, and using least squares analysis to look at the trends from all the parameters. Results and interpretation are still ongoing and in process, so this is by no means a conclusive study. I'll touch on some of the results though, and then some of the future work. So looking first at the GRACE data, so this is just the JPL product. The CSR product agrees quite well, so I'm just showing one for clarity. This is in millimeters of surface water equivalent and is of course centered at 0, so this is the anomaly. And after removing the seasonal and interannual signals, we see possibly a slight declining trend, though it's not large and it's not significant over this 20-year time span, especially with the 11th month data gap. So we'll look at more data sets, but what we can take from this one is that there could be a declining trend, but it's not necessarily conclusive. Looking at the precipitation data, the CRU and the NOAA data sets agree quite well. The CMAP is a little bit deviating from those two. I would attribute this to the fact that the CMAP data incorporates satellite measurements of precipitation as well, while the CRU and NOAA data sets rely mostly on gauge station networks. And what we see is that the CRU and the NOAA show almost no trend at all, while the CMAP data shows a slight declining trend. Again, this is probably looking at the y-axis here, about 12 microns a year declining, so it's quite small. But we can compare that with the GRACE and see that they're both declining, though in a very, very small and not necessarily conclusive way. Adding on the Geodesy snow water equivalent data, this declining trend is about double that of the CMAP trend, going down at about 30 microns per year. So similarly to the last two I mentioned, a declining trend, but not necessarily enough to say something conclusive about that the overall trend in the Mckenzie River Basin is declining. Looking then to the stream gauge station data, you can see on the map here which gauge stations I used for this analysis. And we actually see a significant increasing trend, which is in comparison with the last data sets quite different. So it goes from about -7 to +8% of a deviation from the mean. And so that's, yeah, again, quite interesting when comparing that to the trends looked at previously. So initially we see, for the first 3 parameters here, either we're declining or we're staying about the same. A study from Scanlon et al. 2016 found the declining trend in the Mckenzie River Basin from the I think the JPL and the CSR data as well. But our surface runoff is increasing. So that kind of leads us to a few questions. So the first, where is this excess runoff coming from, if not from a corresponding excess precipitation? So the first 2 answers to that question here are slightly related. You can see in the image to the left, this is just an island off the coast of Yukon in the Beaufort Sea, measuring the permafrost thaw here. So permafrost thaw is happening in the Mckenzie River Basin. The question is mainly how much of it is contributing to this excess runoff, and that's something that will need to be studied more. There are a lot of data gaps here as well, or knowledge gaps. So it's just an interesting thing to point to. As well, precipitation gauge stations are more sparse in some areas of the Mckenzie River Basin than in other areas of Canada that are more densely populated. So is it possible that our precipitation measurements are not accurately capturing a trend that does exist? So that's another question as well. And we can look spatially. This is just a bit of an animation. Each monthly product has had the basin-wide mean removed. So it's basically just showing where there's spatial variation in the monthly signal. Blue being a positive deviation and red being a negative deviation. And after about 2010, so about now-ish, we start seeing even more in the south central eastern portion, sort of a negative deviation existing more commonly, and in the northern area, more positive deviation occurring. So this is really showing us that, to average something across the entire basin might not give us the full picture of what we're looking at. And it's important to look at these local trends as well. So taking an average of 2002 to 2020 of that average deviation from the mean, we can see that we get these zones. So this, again, the south central eastern portion, which is experiencing a negative deviation from the mean, and then the northern part, which looks like it has a positive deviation. We can compare that to permafrost class map. So we see here is that this negative deviation is occurring in an isolated and extensive permafrost zone, while the positive deviation is occurring in the continuous and extensive zone. And that's not to say anything conclusive about the permafrost thaw causing this negative deviation, but just something interesting to look at in the future for sure. We can do the same thing with precipitation and snow water equivalent data. So the CRU, NOAA, and CMAP precipitation records show a bit of a negative deviation sort of in the northern zone, positive deviation in the southwestern area. CMAP doesn't really show much of that at all, and all of the trends are very slight. This is in millimeters of surface water equivalent. And our snow water equivalent actually shows the exact opposite. So we're seeing positive deviations in the north and negative deviations in the south. And this, again, unconclusive, but something to look for in the future when averaging across an entire basin, that we might have these locally concentrated trends or deviations that might be affecting our averages. So there's a lot of people working on studies in the Mckenzie River Basin. The Mckenzie River Basin Board helped put out the State of the Aquatic Ecosystems report, which includes many recommendations for filling knowledge gaps and many calls to meaningfully engage Indigenous communities. Also have seen, even just during this conference, a lot of people working on different studies based in not only the Mckenzie River Basin, but other alpine regions of Canada. I've seen hydrology and geochemists and geodesists, so that's really exciting to see. And then just to sort of touch back on my initial methodology slide. So I went through the pre-processing, the data assimilation, and the statistical analysis. And though we haven't made any distinct conclusions from this study yet, I'd like to tie this back to the Sustainable Development Goals. So the 4 I mentioned before: life on land, climate action, clean water and sanitation, and partnerships for the goals, and just provide some takeaways from at least things that I took away from this study. So first, local efforts to measure ecosystem impact are crucial. When I did research on the ecosystems being impacted by hydrological change in the region, I noticed a lot of variability just place to place within the basin. So that's really important to look at. For climate action, reducing emissions are going to mitigate the consequences of the increased temperatures. In the session, we've talked a lot about sea level rise and the different scenarios for different amounts of emissions. And it's important to, take action to reduce emissions, which will mitigate consequences of, say, things like permafrost thaw, especially in this basin. We're also seeing, in terms of clean water and sanitation, a dramatic sea level, or not necessarily sea in this case, surface level variability. So when we have industry in this area, which can provide contamination to these surface waters, understanding the local hydrology and how those levels are fluctuating will be important to mitigate those contaminants as well. And finally, in terms of partnerships for the goals, traditional knowledge from Indigenous communities is incredibly important when we're looking at especially these areas where populations are sparse, but they've been there for many thousands of years. And finally, it's just important for us to share our research with each other and with the government as well to make sure that we can get effective action to come out of our science. So thank you so much. And thank you to many different sources of funding for my research. I'm very grateful. If anyone has any questions or comments, anything, that can happen now.
Thanks, Stephanie. So the floor is open for questions. If we have questions, you can type them in the chat or just unmute yourself and ask Stephanie. Okay, no questions. So that concludes our session. Thank you to everybody and to all our speakers for attending and sharing your research and your thoughts on geodesy and how it links to the UN Sustainable Development Goals. And on behalf of Calvin and myself, we hope this is a continued part of the discussion and not the end of it, and hope to see many more topics and sessions like this in future conferences. Calvin, do you have anything you want to add?
No, thank you very much, Georgia. I think you did all the work. So yes, it was very, very interesting session. Thank you for everybody. Thank you everyone for the presentations.
Okay, thanks. Bye now.